Thank you. Thank you for the invitation to speak. I don't need to introduce you all the industrial wonders of quantum key distribution. There are networks in many countries nowadays. China is leading the world, but there's a lot of deployment. And there are probably more than 10 companies that are making the QKD systems now. So I'm going to talk about the engineering of making sure the systems are free of loopholes and certified. So the topic, this is certification, and you've seen the pictures from the previous speaker. This is, by the way, he mentioned that the nodes of the backbone are connected to metropolitan networks, and this is, for example, a network in Hefei. It has 159 end users and 8 nodes in the metropolitan network. So it's just the example of this. And this is just one city in China. And the problem we face is that with this scale of deployment and with actual use starting, you need to certify the systems to make sure they are secure. And quantum cryptography is unbreakable in principle. But these implementations are imperfect. They're quite complex. So a typical implementation contains maybe 20 optical components. Optical components have imperfections. It contains a lot of electronics. Electronics has imperfections. And it contains software, which is large, and it contains also imperfections. And it's made by engineers, by humans, who not always understand how to make things secure. So it has many things that are not envisioned by the theory. And based on those imperfections, you can very often break the security of quantum key distribution. At present, we know more than 25 different types of imperfections. Each of them potentially breaks security. And to make sure that we have secure systems, we introduce, or most countries have in place, a certification system for cryptographic tools. All the classical cryptography that is in use today has been through certification, because the implementation imperfections are not unique to quantum cryptography. In classical cryptography, there are also implementation imperfections. So to deal with this problem, the national government, together with the National Security Authority, establishes a certification standard, which is a set of legal requirements that says that which things have to be checked in a certain type of cryptographic system. It sets the requirements for a certification lab. And there is at least one, possibly more, accredited labs in the country that can, according to this certification standard, perform the certification. And the manufacturers submit a sample of their equipment together with internal engineering documentation to this accredited lab to be certified. And after a few months, hopefully they get a certificate saying that it passes all the requirements in the standard. So what should the standard check? The standard says basically two things. First, it checks that the system implements what it claims to implement. So if the system says it is a twin field protocol QKD system, the lab opens it and sees that it actually does the twin field QKD and not, for example, 2 hard drives with a shared key or something stupid. That it actually implements the protocol that it claims, and it has the functionality, and it provides the key rate and the key management and the interface. So all those things. And the second thing the standard checks is, of course, that the system has all the proper countermeasures against the implementation problems. And this is half the certification task. And before the company submits the system for certification, the manufacturer has to make sure that the system actually has all the countermeasures in place, because it's quite stupid to submit to certification without preparing your system. It's going to fail the certification. So the company first makes this homework and tests the system themselves and checks and plugs the loopholes it finds. So to start this work, a few years ago in Russia, my lab partnered with a manufacturer, Curate, it's a Russian manufacturer, And we analyzed this, the security of their commercially developed QKD product, which is a high-speed 312 MHz QKD system. And there we did this preparatory work with the company, found problems. The company plugged loopholes, and then we used this work as a basis for establishing a national certification in Russia, an accredited lab. Briefly about the system. So the system is standard prepare and measure system. It has a laser running at 312 MHz. It's a decoy state BB84 system, so it has intensity modulator that prepares vacuum, decoy, and signal states, 3 intensity states. It has a polarization modulator that prepares 4 polarization states. This quantum state goes through attenuators, so it's a weak coherent pulse. Attenuated pulse goes through some isolators and through the communication channel. At the receiver side, there is another polarization modulator that actively chooses the measurement basis at Bob, and 2 polarizing beam splitter, and 2 single photon detectors that distinguish between the 2 polarization states. Also, there is a synchronization channel at a different wavelength. And when we analyzed the system, we found 15 potential implementation problems with this optical scheme. They are listed here. Some of the problems were quite serious. So, for example, we found 4 loopholes, 4 attacks, which we sure confirmed that they existed in the system. And they were exploitable today, so there was a high risk. So the exploit could be built today with all off-the-shelf equipment. You don't need future technology to do the exploit. And for those 4 problems, the company, of course, had to implement countermeasures before the system is submitted for certification. And we found some more problems, which ranked a little bit lower by risk. For example, there were attacks that are in principle possible, but we don't know how to do the attack, or they require future technology, so those are ranked a little bit lower. And after this work, after the company has implemented countermeasures for most serious problems, we have recommended that there are about 10 certification tests for possible attacks. And then, okay, so let me show you some of those issues, just 5 of them. I don't have time for all. So one typical problem in a system that has single photon detectors and is not measurement device independent is that the single photon detectors are blindable and controllable by bright light. This is a well-known attack. And indeed, we tested the single photon detectors. They are sinusoidally gated detectors, and we could blind them and control perfectly, so the system is not secure. The detectors had a rudimentary countermeasure already implemented, a photocurrent monitor that measures the photocurrent, and this photocurrent monitor correctly catches continuous wave blinding, so we could not continuously blind the detectors. There was an alarm in the system. But the photocurrent monitor was slow, the sample rate was low, and we could manage to do pulsed blinding and still control the detectors. So the company did a next version of the detectors, updated the photocurrent monitor with much higher frequency, and now this detector is produced and it still has to get to my lab to pass the final test, but we think it's going to pass. Another notable problem, so one attack, if can take and launch a high in brightness pulse into the communication line towards inside Alice. This pulse is going to pass through all the isolators and attenuating components, reach the modulators, and it gets modulated by the same state that prepares the quantum state. And there is always some back reflection from components. So a fraction of this pulse is going to reflect back and exit into the communication line. And as long as Eve measures at least 1 photon exiting back, remaining, she can externally read the state of the modulators. This attack does not interact with the quantum state, so in theory it does not introduce errors, it just reads the modulators externally. To protect against this attack, and the maximum energy of this input pulse is limited by the size of the core of the optical fiber. The fiber can only transmit up to some 20 or so watt. Above this, the material ionizes and the fiber explodes. So there's a physical limit of how much power EVE can inject. And what we need to protect is to measure the transmission loss through each component on the way of this pulse and add together the transmission losses. And if we find out that the pulses are attenuated so much that usually no photon exceeds, so the mean number of exciting photons is sufficiently low, way below 1 photon, then the system, we can calculate the key rate and make the system secure against the Trojan horse attack, so passive protection. But the difficulty is that EVE is not limited to your operational wavelengths. She's probably not going to attack at 1550. She will pick another wavelength, anywhere from UV to beyond 2 microns, where this path has the lowest attenuation. So you actually need to characterize each component in a very wide wavelength range. This is what typically even metrology labs don't do. The manufacturers say nothing how the component is going to behave at far away from the designed wavelength. So you need wideband characterization. Another light injecting problem, EVE can also inject light close to the operating wavelength and seed the source laser with some radiation. And this seeding changes the characteristics of the lasers. The laser can increase the pulse energy, or if the wavelength is closed but not quite at the operating wavelength, it can hijack the emitting mode and change the wavelength of the laser. So there are attacks based on that. And of course, the protection is also passive. You need to calculate how much attenuation and make sure that the power that reaches the laser cannot do anything bad. So it's low enough at this point. Again, you need to characterize. Laser damage problem. So you know that if EVE shines sufficiently bright light at anything, it's going to blow a hole in it or melt, change the component. And it has been shown that EVE can, for example, burn attenuators and permanently reduce their attenuation, which of course is bad because then the system begins to emit multi-photon pulses and the security is gone. And the protection against the laser damage attack is to add one extra component at the input that is going to work as a power limiter. And if the power becomes too much, like a fuse that blows up and breaks the channel. And this component has to protect the next component from damage and everything else. So it takes all the damage by itself. And another problem, notable problem, is intrasymbol interference. In the source, in the modulators and the laser, they are working at a high rate. And because of bandwidth limitations of the driving electronics, the pulses states they emit are not quite independent. The security proof requires the emitted states to be independent, but actually the states have correlations between them. So the currently emitted state is a little bit affected by the previous states. And this intrasymbol correlation reduces the key rate. It is a security problem. So what you need to do is to characterize intrasymbol correlations and then apply a security proof to see how much secure key rate remains in the presence of correlations between the states. So this is about what we have suggested to the National Security Agency that the certification lab should contain. It should have 5 test benches. So one test bench is the wideband spectral characterization. This is needed for several attacks. And it characterizes the component in a very wide wavelength range for their transmission. The second station is detector testing. Of course, you need to test single detectors against different attacks against detectors. Intrasymbol correlations and state preparation flows are also tested on a state preparation characterization station. Single photon detectors based on avalanche photodiodes emit a backflash, so you need another station that measures the amount of photons emitted by single photon detectors. Of course, when they emit, this is another leakage channel. And you have to test your power limiter against laser damage that it performs properly, so you have to have a laser damage station. I'll show you some of those stations. The wideband characterization station consists of a high brightness supercontinuum source, light source, several watt, spread over a wide spectrum from 100 to 2300 nanometers. This is its spectrum. Then you connect the device under test, you shine the light at device under test, and you measure what comes through using a spectrum analyzer. We use two different spectrum analyzers that together cover this wide spectrum. And the sensitivity of the spectrum analyzer, this is the noise floor, and you see that we have, depending on the wavelength, you have anywhere between 30 and 70 decibel dynamic range. So within that limit, you can characterize the transmission. And if the transmission of the component is higher than the dynamic range, then you just conservatively assume that it's transmitting at the noise floor. We tested this test bench on three generic configurations of a typical QKD source. So those configurations are not from this commercial system, they are just some typical source configurations. They have modulators, so if can try to do Trojan horse attack against modulators, and it has two variable optical attenuators, three isolators, and the first configuration. The second additionally has a dense wavelength division multiplexer to do the filtering, and the third configuration, instead of DWDM, has a fiber Bragg rating based filter. And we characterized each component, added the attenuation together, and for a Trojan horse attack, this white curve is the total attenuation that the Trojan horse pulse will see. And you see that at one point it reaches the attenuation is less than 200 decibel. And if you look at the security proof, the security proof predicts that at this much attenuation, the key rate drops so much that the system practically stops generating the key. So this is too little attenuation. The second configuration, at some wavelength ranges, this WDM increases attenuation, but unfortunately not at the point of interest, so there it remains the same, also bad. And only the third configuration raises the total attenuation everywhere in the range to be at least 300 decibel, and this is enough, so your performance is close to perfect. So only this one will be right. The intra-symbol correlation. So how the one pulse is affected by the previous pulses. To test the intensity energy of the pulses, the scheme is very simple. You take your QKD system as is, and you reduce the attenuation to 0. So you either remove attenuators or you command the attenuator to set the minimum attenuation. And then at the output of the system, you measure the now bright states using a photodiode and a fast oscilloscope. So this is the oscilloscope, this is photoreceiver, and then you use software to analyze the correlations. Now, this is the oscillogram of the vacuum decoying signal states emitted, just on sequence. And you can see that this decoy state has a certain amplitude, and this decoy state has a different amplitude, and this decoy state has a different amplitude. So clearly they are different, and they are affected by the prehistory, what preceded them. So if you integrate the energy and plot the energy distribution on this decoy, so on average, all decoys have this gray distribution. But if the decoy was preceded by a signal pulse, it tends to have lower energy. But if it was preceded by a decoy or vacuum pulse, then it tends to have higher energy. So those distributions are clearly shifted relative to each other. So now if you plot it on this kind of diagram, this is your decoy state on average at 1 normalized energy. And if it was preceded by a signal state, then it has lower average energy. And if it was preceded by the other two states, it has higher average energy. But you can also look at the higher order correlations. What if the history contains now not one, but two pulses? Now there are 9 different levels. And you can see that for decoy state for this particular system, you can get plus minus 4%, which is a big deviation. In this paper, we have up to fifth order correlations measured. And if you apply a security proof for this case, developed by the group of Marco Scorzi, then you can, in the presence of those correlations, calculate the secure key rate, and you see that the performance drops, but you still get secure key and can operate up to 100 kilometers, which is good, probably secure. So there is a security proof that can be applied. Laser damage. I remind, in the laser damage test bench, we test the performance of the power limiter. At the input, the power limiter has up to several watt light, and its task is to restrict the amount of light passing to a safe level that cannot damage the next component under all circumstances. So it either attenuates or just breaks the line. So the test bench contains of a high power source, fiber amplifier that provides you the light to be tested, and also some signal lasers that can help you to measure the transmission of this component under test. So we tested some commonly available cheap isolators, fiber optic isolators, and they appear to be a good protection against continuous wave attack. The isolators, they reduce under several watt continuous wave illumination, they reduce their isolation a little bit, but still have sufficient isolation to protect the next component that follows them. And if too much light is applied, they literally burn. So this is unencapsulated, you see its chart. And they burn in a nice way. They become like a fuse. They break the line. They become very high attenuation. And of course, the system is broken after this, but at least it's secure. But, so for a while, we thought that the isolators are a good component and the problem is solved. But the problem is, Leaf is not limited to 1550 nanometers continuous wave laser. She can use lasers at a different wavelength, and she can use pulsed lasers. So when we tried to test it with a pulsed laser at around 1061 nanometers, we saw a different result. So this is a fancy laser. It's a fiber laser that has a ring oscillator, and it has two stages of amplifiers. And in this configuration, it produces 360 picosecond pulses with an average power of 1.3 watt at 1 megahertz. And in a different configuration with one-stage amplifier, it uses a chirped fiber bright grating to do the pulse compression, and there the pulse is less than 30 picosecond wide at only 17 milliwatt mean power. And when we applied those pulses to two isolators, the isolators temporarily reduced attenuation by 20 dB. So this is temporary, they recover after this. And at the same time, they kept the forward transmission, so that they still transmitted all the light that comes to them. So that's not good. If the power is higher, of course, you can burn them, and they reduce the isolation even more by 30 dB, and the forward transmission only increases by 10 dB. So again, a bad result. They are not doing their job. But the most interesting result was with 17 milliwatt 30 picosecond pulses. When we applied dot light to the isolated remained the same transmission, less than 1 dB, but it temporarily lost its isolation by 20 dB at only 17 milliwatt illumination. So clearly we need to test more with different lasers. And finally, let me present a new attack. I mentioned that when you do laser seeding, you can do laser seeding using light very close to the operational wavelength of your laser, to 1550 nanometer. But then we tried to apply light at a very different wavelength. We applied light at 1310 nanometer, and at this wavelength, the light cannot do seeding. The laser has no gain at 1310 nanometer, but instead it did external laser pumping. So in a semiconductor laser, it absorbed and it increased the population inversion. The quantum efficiency of the laser raised, and because of this external pumping, in addition to electrical pumping, when this pumping light is applied, at 1.6 milliwatt pumping light at this point, the pulse energy emitted by the laser increased by 10%. So we just externally pump the laser, partially. And also, the pulse shape changes. The shape of the pulse emitted differs when in the presence of pumping. So this is another attack. Thankfully, in this particular commercial system, the laser pumping attack is not a danger because the power to do the pumping is quite high, is quite high, and the existing isolation will already be enough to attenuate it. But in different QKD systems that do not have modulators in the source, such as, for example, passive state preparation schemes, they don't already have protection against this attack. And then this attack becomes a valid point to check, and you need to see if you need to add isolation and attenuation even to the systems that are not susceptible to Trojan horse attack. So what is happening in this field? There are two good resources to look at if you want to read more about attacks. There is an excellent review published by a German security agency. It's practically a catalog of attacks and countermeasures, quite a big paper. And it lists everything with all the references, everything known. The International Standards Organization has released an international standard on security testing for QKD already 2 years ago. And it includes a general approach to certification against many known attacks. And presently, the European Union is running a development project called Nostradamus under EuroQCI. And that project, so look, Russia has already introduced its certification because it passed all this methodology you see in this presentation to the Russian security agency. And I think they are using it to certify Russian QKD systems now. But Europe is only now commissioned the project and currently is doing the same development that we have done in Russia over the past few years, hopefully better. And by 2028, in Europe, there will be an unaccredited lab that can test QKD. Thank you.